students. Today we will talk about Stern-Gerlach experiment. This is an experiment which was used to determine the spin of an electron. So it helped us in determination of electron spin. The experiment was done in 1921. Until then, we knew about mass of electron, charge of electron, but through this experiment, we got to know about another intrinsic property of an electron, and that is its spin. The entire experimental arrangement is like this. Silver atoms are heated in an electric oven. So this is an electric oven in which silver atoms are heated. They are melted and they evaporate. After that, they are passed through two slits to collimate the silver beam. Once this happens, then the silver beam is subjected to a non-uniform magnetic field. Now, how do you understand that the magnetic field is non-uniform? This is by the shape of the poles. If this is the north pole, its shape is like this, and if this is the south pole, its shape is like this. From the shape of the magnetic poles, we can assess that this silver beam is subjected to non-uniform magnetic field. After that, this silver beam hits a photographic plate at the end. One of the reasons of using this silver beam is also that since it is a photosensitive material, it is going to make an impact or create an impression on the photographic film. Now, if mu is the magnetic moment associated with each silver atom, then on passing through a magnetic field B, the torque experienced by the silver atoms would be mu cross B, right? And due to this torque, they will align themselves at a particular direction with respect to this non-uniform magnetic field, and as a result of that, they will gain certain potential energy, and that potential energy U will be given by minus mu dot B or mu B cos theta. Consequent to which we can evaluate that the force is equal to minus delta U, and that is equal to d by dz of mu B cos theta. This minus sign goes with this and we are left with this alone. And we see that suppose if the these silver atoms are moving along x direction, the change is along the z direction. They will reorient themselves at a different direction. This magnetic field has been held perpendicular to the direction of the silver beam. Now, force is equal to mu cos theta dou B by dou Z. Consequently, we can write that acceleration is equal to force by mass, and if capital M denotes the mass of each silver atom, then acceleration is mu by m cos theta dou B by dou Z. Now we are mainly interested in seeing that how far do these silver atoms reorient themselves on being subjected to this non-uniform magnetic field. So we are interested in finding the orientation along z direction. So the distance traveled along z direction obviously will be given by half of at square. We have already found the acceleration, that is 1 by 2. For acceleration we can write it is mu by m cos theta dou B by dou Z, and if L is the length covered from one point to another and T is the time taken, then the time can be written as distance by velocity square, right? So then we can take it to another page. So from this we can write that Z is equal to mu L square by 2m cos theta dou B by dou Z. And of course this V square is here. For this V, we can write that this is equal to, thermodynamically speaking, this is 3 kT by m. And we are also interested in this parameter because we have actually melted the silver beam at some particular temperature of the oven. So we'll substitute this V over here and we get Z is equal to mu L square cos theta by 6 kT dou B by dou Z. So that is the final displacement of the silver beams along the Z direction once they are subjected to a non-uniform magnetic field, and this is the resultant expression. Now if B is equal to 0, Z is equal to 0. In that case, we are going to get a straight line on the photographic plate, and in case this B is uniform, then dou B by dou Z is again 0, and again the distribution of silver atoms will be given by a thin fine line on the photographic plate. Now when the magnetic field is non-uniform, which is so in the present case, we get a distribution like this. The silver atoms in which the valence electrons have a spin up orientation gather or collect at one place, and those with a spin down orientation gather or collect at a separate place. So one peak is for spin up and another is for spin down. So the importance of this experiment, once again I am reiterating, was that it helped us to obtain another quantum number for electron, and that was it is spin. One collection of atoms for spin up orientation and one collection of atoms for spin down orientation, which happens once we have subjected the silver beam through a non-uniform magnetic field, and that's all about it.